Why do almost all spacecraft travel sideways along a flat plane? Instead of simply flying straight up into deep space? Imagine standing on Earth and looking up into the vast night sky. Space surrounds us in 3 dimensions: up, down, left, right, forward, and backward. Yet, if you look at how planets, moons, and space probes travel, they all share a remarkably flat orbital plane in our system. Astronomers call this flat cosmic disk the ecliptic plane. It seems natural to ask a fundamental question about this structure. Why don't we build rockets that fly straight up above this plane?
Why not take a shortcut out of the solar system by soaring perpendicular?
To an untrained observer, heading up into empty space appears like the shortest path.
But in orbital mechanics, flying up is one of the most expensive journeys. A rocket attempting this trajectory faces invisible velocity barriers and extreme drag. What physical laws force our entire solar system into a flat disk? What hidden orbital tax must a spacecraft pay to break free? Today, we explore the fascinating physics behind why vertical escape is nearly impossible. To understand why flying up is so difficult, we must go back in time. We travel back 4.5 billion years to the solar system's birth. Our solar system originated as a giant, spherical cloud of interstellar gas. This cosmic cloud of dust was floating peacefully in the dark expanse of space. As gravity pulled the cloud inward, its particles began colliding rapidly. These particles were interacting randomly, bouncing off one another in all directions. Every particle had its own random speed and direction in 3-dimensional space. However, as the cloud condensed, a key physical law began to dominate. The conservation of angular momentum took control of the collapsing system. Collisions between particles canceled out movements pointing up and down. Only the net rotation axis remained untouched by these constant particle collisions. Over millions of years, the spherical cloud flattened into a thin protoplanetary disk. This spinning disk of dust became the cradle for all future celestial bodies. Every planet, asteroid, and comet that formed inherited this shared orbital plane. They all inherited the same direction of motion from that ancient spinning disk. Earth itself is currently zooming through space along this flat plane. Our home planet travels at roughly 7,000 miles per hour.
This shared orbital speed is both a massive advantage and our greatest obstacle.
When a rocket sits on a launch pad, it isn't standing still.
The launch pad itself is moving rapidly through the solar system. It is already moving sideways around the Sun at Earth's orbital speed. This sideways speed is a massive 30 kilometers per second.
If you launch a rocket straight up, perpendicular to the ecliptic plane,
that massive sideways speed does not simply vanish into thin air. The rocket retains Earth's 6,000–7,000 mile/hour sideways momentum.
To fly truly straight up, the rocket's engines must burn massive amounts of fuel. They must use this fuel just to cancel that tremendous sideways momentum.
Canceling 30 kilometers per second of velocity requires an astronomical amount of energy.
It requires vastly more energy than escaping Earth's own gravitational pull.
If the rocket doesn't cancel that sideways speed, its path simply tilts. The trajectory bends into a wide, highly inclined orbit around the Sun.
It continues looping around the Sun, unable to break away into deep space.
Without enormous propulsive power, it remains trapped in the solar system.
We are locked into a cosmic highway moving sideways, making vertical escape costly. Since current rocket technology cannot carry enough fuel, we need clever solutions. How do scientists explore polar regions without using brute force?
When astronomers wanted to study the Sun's mysterious polar caps, they faced this problem.
Using direct thruster power to reach the poles was completely out of the question. Instead, brilliant engineers utilized a clever orbital maneuver called gravity assist.
They launched the probe sideways toward a massive gravitational target.
The target was the giant planet Jupiter, a massive gravitational engine. The probe swung deep into Jupiter's massive gravitational well.
Scientists used Jupiter's immense orbital energy to alter the spacecraft's trajectory.
Jupiter's gravity slingshotted the spacecraft out of the flat ecliptic plane. The probe was redirected into a highly inclined polar orbit around the Sun. Without using planetary gravity assists, achieving such orbits is practically impossible. It would require rocket sizes that are far beyond our current capabilities. Gravity acts as a natural cosmic slingshot, bending orbital paths upward. This represents an elegant victory of mathematical physics over brute force. It shows how clever navigation can overcome the limits of traditional propulsion.
As propulsion technology advances, new methods for out-of-plane travel are emerging.
Traditional chemical rockets are severely limited by the heavy weight of fuel.
However, alternative systems like ion propulsion offer continuous, low-thrust acceleration.
Another revolutionary concept is the deployment of giant, shimmering solar sails. Solar sails utilize the gentle, relentless pressure of incoming solar photons.
By angling the sail against sunlight, a spacecraft can continuously alter its path.
It can gradually change its orbital inclination without burning a single drop of fuel. Over years, a solar sail can climb higher above the planetary disk. These advanced concepts may one day allow us to navigate the three-dimensional cosmos. Breaking free from the flat planetary plane opens new frontiers for deep space exploration. Flying up in the solar system reveals the subtle elegance of physics. What seems like empty space is governed by invisible momentum vectors. Our flat solar system is a permanent memory of an ancient spinning dust cloud.
Overcoming these natural orbital limits showcases human ingenuity and mathematical skill.
As we develop solar sails and advanced propulsion, the three-dimensional cosmos awaits. Nature presents obstacles, but physics provides the keys to unlock the universe.
Thank you for watching, and keep exploring the wonders of the universe.